All right, folks, so I passed back a whole heap of stuff here. Included in that were your test twos. The scores that are on your test two papers are just your raw numbers. There's been no adjustments made. So there are, we talked about volunteering for the Math and Med Open House. 3 people did that. So you can thank Kylie, Mia, and Adriana from 8th Hour for doing that for you guys. So you guys all have a +3 onto the test points, not percentage, test points. So that's like 5-ish%. So the +3 from that, everybody gets it for those 3 people doing that. Great, good job, thank you everybody. If you're a guide, that's different. You know, like I know that some of us had to be there for other reasons. This was a different thing. So there will be some additional curve on this. Right now, prospectively, that looks like kind of in that 6-7% range would be added on also. I'm gonna wait, I still have to score Caroline, so I wanna look at kind of where that lands, but I think it'll probably be in that like 6, 7, 8% range. Will put us like into the low 80s as a class average, which I think is acceptable. So to just give you a heads up as to like, those scores haven't come in yet. I'm still waiting on Caroline, but I wanted to pass these back because I've been sitting on them for long enough, and I'm sure that you guys were curious to see like how you did. So that's kind of how that'll work. So I think in this section, I think it was Maddie that had the high score for you guys in here. Yeah. So the raw high score was a 92 from both sections. There are a couple others, 91s, 92s, or 90s in that neck of the woods. So we'll let you take the test home and look over things. We'll take questions from that next time to give you a chance to like look over things and see what you did or didn't do or what my comments were and all that kind of thing. I don't want to chew up a bunch of class time now when you guys will, I'm sure, sit down and gossip about it later, so, which is fine. You should do that. Everybody good? Okay. And again, I probably by the end of the day I'll have scores in. I just want to grade Caroline's before I make a decision between like 6, 7, or 8. Not that it's all on you, Caroline, but I'm just being upfront with where we're at. 7 would be my expectation as to where that'll land. Okay. All right. Let's pick up then where we had been left off on last class. I'd asked you to work on that. How's this going to be a problem? I'd asked you guys to work on that derivatives handout, the packet. Had just 20 questions or something. If you guys can take that out for a minute. Now I put my worked out solutions into my Notre Dame on the OneNote. Now, word of warning, you know, like I wrote out those worked out solutions. I didn't have a chance to proofread anything or double check anything. I was just, you know, like in a rush. So if there are mistakes in there, there could be. And if you find anything like bully you, like please let us know. Let's take a look and decide if it's a mistake or not. If it is, Great job locating a mistake. It's a credit to you. So as soon as this wants to see if this will work now, we can try to do that and take some questions from there, if there are any. Does anybody have questions from the packet that you want to ask about that the worked out solutions didn't satisfy? Did that fix my problem? Looks like maybe. There we go. Number 10. Great. All right. Oh, yes. Number 10's a good one. Okay, come on now. All right. So when I look at number 10, this looks mucho overwhelming, right? At first glance, I look at this and I go, okay, well, let's see. I see 1, 2, 3, 4 quotient rules right away, and then a big quotient rule, that's 5, and then 2 chain rules for the quotients inside of the fractions, and like this does not look like a problem where Mr. Kulik says that you can do this with no more than one of the chain product quotient rules, at least the way it's currently presented. The key here is going to be doing some algebra beforehand, and you can really like take a like a sword to this problem and take it from something that looks completely infeasible and overwhelming down into something that's quite manageable. So the simplest, and I think really the best way, almost always, to deal with one of these complex fractions, a fraction inside a fraction problem, is to multiply the top and bottom by the least common multiple of the small denominators. So if I look at the small denominators, I see x minus 1, x plus 1, x plus 1, x minus 1. The least common multiple of those is x plus 1 times x minus 1. So I'd start by doing this. When I multiply x plus 1 times x minus 1 to that first fraction, the x minus 1's cancel. And I'm left with x plus 1 times x plus 1. When I multiply it to the second fraction, the x plus 1's cancel. And I'm left with x plus 2 times x minus 1. No more fraction in the numerator. When I multiply it to the small fraction in the denominator, the x plus 1's cancel. I have x minus 3 times x minus 1. And then when I multiply it to the second one, the x minus 1's cancel. So I have x plus 3 times x plus 1 that are left. Notice by doing that, I've cut 4 quotient rules out of this problem. That is a good deal. That's a good stinking deal, guys. Although now what have I replaced it with? 4 product rules. But these are all easy product rules to eliminate as well, because all I have to do is multiply these out, do a little bit of foiling, and I'll cut out the product rules as well. So just foiling everything out. Is everybody okay there? Notice that I distributed the negative through on the x plus 3 times x plus 1 as I FOILed. So if I combine my like terms, 2x squared plus 3x minus 1 on top, and on bottom, a whole bunch of nice stuff happens. Pew, 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 pew. So far, so good. Stop me if I'm going too fast, or if I do something you're unsure about, or if you think I've made a mistake. Any of those things are worth speaking up on. Now, notice I've cut out the 4 product rules now. I'm down to just like 1 quotient rule that would have to be done. But do I actually even need to do a quotient rule? Because that denominator is a monomial, I can keep algebra in. And write it as 3 fractions with a common denominator. And then just reduce. And now I'm ready to take the derivative of this guy, which is now something conceivably I can do with my head. Look at how valuable that algebra was, right? The derivative of negative 1/4 x is negative 1/4. The derivative of negative 3 over 8 is 0. The derivative of 1/8 times x to the negative 1 is going to be 1/8 times negative 1 times x to the negative 2. And that's a spot where I could stop. Did I make a mistake on the answer key on this one? This feels like not what I got on the answer. Do you remember? Nobody looked? Or just nobody remembers? Either is fine. Oh, that's not what I wanted. No. What did I say here? Oh no, I did get the same thing. Oh, good. Hey, look at that. Just double check that. But like, how much nicer did that turn out to be than like kind of an impossible task at the beginning? Else. It would reduce down to the same thing, for sure. You'd have a little bit more reducing work to do. But if it's a free response question where you don't need the fully reduced answer, who cares? If it was a multiple choice question, I promise you that like the result you have from that is going to have some cleanup to do before you get to one of the choices, but not wrong. In fact, it wouldn't have been wrong to just dive right in and been like, okay, well, I have like 5 quotient rules ahead of me. Like, might as well get going. Yuck, but okay, you could have gone and done that. I wouldn't have wanted to, though. Pass. Again, one of your best and most time-saving tricks is going to be noticing when you have a denominator that's a monomial that allows you to cut out having to do a quotient rule. That is a nice thing to look for. That'll be a common trick that you'll see, particularly when you see like AP stuff on the multiple choice section, is can I find a way to cut out having to do the quotient rule? And sometimes you can't, but oftentimes there's going to be a backdoor to the problem that allows you to kind of skirt around having to do some of the nastier algebraic manipulations. Adrian, how would that feel okay?
Yeah.
Okay. That was your question, right? Okay. What else do you guys want to look at? I'm going to limit you to one from the back page, just for time's sake. If anybody's brave enough to be like, I think I want to ask about that one. Just for time. What? What I'm going to do then today, we're going to continue on talking about section 3.5 and implicit differentiation. So here it says find y prime if sine of x plus y is equal to y squared cosine x. So we'll just start by taking the derivative of both sides. Now suppose you could have used your angle sum formula to rewrite sine of x plus y into like, I think it's sine x cosine y plus cosine x sine y, I think is the angle sum formula, but like, that. But it's not unreasonable to do that. I don't think it helps us really much. Everybody's okay? All right. So to take the derivative of sine xy, what do we need to use? Chain rule. Okay, so the outside function is sine x, so the derivative of sine x is cosine x. And then the stuff on the inside, and then times the derivative of the inside, right? The derivative of x is 1. And the derivative of y with respect to x is dy dx. Or you could write it as y prime if you prefer. I like to write mine all dy dx's because sometimes the prime symbol just kind of gets lost on me. The dy dx, so it's hard to lose track of. So far, so good? Peyton.
Can you explain again why you think dy dx for y?
Yeah, so, you know, like before, if we had like y equals x and we take the derivative of that, we'd write like dy dx is equal to 1, right? Whenever I differentiate a variable with respect to a different variable, it's going to create a differential, like a d whatever. Anytime you do that.
Why do we not care about
okay? And whatever this variable is going to be that variable, and like whatever that is whatever that is. Does that feel okay?
Yeah.
So we've been doing it the whole time. We just didn't like make a thing about it, right? Is that enough?
Yeah.
Okay. All right. To do the derivative of y squared cosine x, what do we need to use? Not a chain rule, product rule, because there is multiplication going on between the two functions, right? So we'll have y squared times the derivative of cosine, which is negative sine x, plus cosine x times the derivative of y squared, which is going to be 2y dy dx. Is everybody so far so good? Okay. Now, what I noticed is I have dy dx in two different locations. So to get the dy dx in one spot, I have to get the dy dx on one side, factor off, and divide the other stuff to the other side, right? So we will distribute through my cosine xy. So far, so good, everybody? So I'm going to subtract the 2y cosine x dy dx to this left side. I'm going to subtract the cosine xy to the other side. Everybody feel okay with what I've done? At this point, I'm just going to take an aside here and mention that when we're writing these cosines, make sure that we're including variables. Some of us, when I was grading some of the last homework quiz, I think, had a lot of people dropping variables and they're writing their sines and cosines. Got to make sure you're including them, particularly now where we have different variables for x and y. Okay? And on a test or whatever kind of setting, I would make a deduction for dropping variables from a cosine function or something. Everybody's okay? Okay. You know what I mean, right? And it's easy to do, especially like when you're in a hurry or whatever. I get it. But we got to be careful that we're not doing that. So I factor off the dy dx. Now that, since that dy dx is in one place, I can just divide both sides by the cos xy minus 2y cosine x. That is probably as good as we could hope to do with that. Feel okay? Very algebra-y, right? If you're like an algebra fan, like this feels good. It's like, I like this. All right. Here we're asked for the second derivative. So let's see how to handle that. So we start the same way. I'll start by taking the derivative of both sides. Now this is a fairly nice, well-behaved function, right? So far, so good. So we'll subtract the 4x cubed from both sides and divide by 4y cubed. And when I reduce the 4s, I get my derivative as that. So far, so good. I'll hold on to that. We'll need that again. But now I'm going to keep going. And take the derivative again now. Everybody's okay? Need a second derivative. This is me doing this, starting the second derivative. What's the derivative of dy dx? The derivative is d squared y dx squared. That's the way you write that. And then to take the derivative of negative x cubed y over y cubed, what do I need to do? Quotient rule. Okay, so that's bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. So far, so good. Okay. The derivative of negative x cubed is going to be negative 3x squared. And then got a negative of a negative, so I'm just going to write a plus. And then the derivative of y cubed is 3y squared times dy dx. Does everybody feel okay? Now this answer is not complete because we don't want dy dx in there, Alice. Can you speak up?
Why would it be x cubed y squared instead of 9x cubed y squared?
Because I'm only taking the derivative of that piece,
Okay.
right? Is that okay? Okay. All right. So our second derivative answer isn't quite complete because we shouldn't have a dy dx in it. We want it to just be in terms of x and y. That's why we made a point to highlight our first derivative answer because we're going to come back and need that again. So I'm just going to make that substitution now. Everybody see what I did there by dropping in the first derivative? And you can do a little reducing here. Right? So I can do that. Everybody agree? And then I'll multiply the top and bottom by y to get rid of the fraction inside of the fraction. I want to point out that at this point you could have been done if it was a free response question. If it's multiple choice, I'm going to keep going and get like a fully simplified answer. just so we can see kind of like what that would look like. So this would be like our, like a multiple choice style answer. Does that feel okay there? It's algebra-y. You got a lot of algebra to sort through, but that's okay, right? Like, in fact, probably most of us feel like this is more my strength than maybe the super conceptual piece. Is like I can grind through them algebra and push them symbols. Like I'm real darn good at that. All right. So we're going to introduce to you guys now another set of derivative shortcuts for the inverse trig functions. So the derivative of sine inverse x is 1 over the square root of 1 minus x squared. The derivative of tangent inverse x is 1 over 1 plus x squared. And the other 4 are collected down in the table below. Here's the bad news, guys. We expect you to have these memorized. Yup. Oh, Mr. Kulik, are you joking? No. And I'm going to prove maybe just this one of them so you can kind of see how this is done. Oh, no. Oops. That's not what I want you to do. Because there is a type of problem much later on in second semester that uses basically the same idea as this proof. Yes. Of course. So we know that if theta is equal to sine inverse of x, then that represents the triangle with acute angle, or the right triangle with acute angle theta, where the opposite side is x and the hypotenuse is 1. Everybody's okay with that? And then I can solve for this missing side then, because I know that x squared plus y squared is equal to 1. Now, technically, that's plus or minus 1 minus x squared, but since I'm dealing with a length inside of a triangle, I'm going to drop the minus possibility. Since it's a side length of a triangle, it can only be positive. Everybody so far so good? All right. How does this go after I've set this up? Okay. So if I have like sine theta is equal to x, and I do like sine inverse, nope, other way around. If I have theta equals sine inverse of x, and I do the sine of both sides, there's an easier way to do this. Let's not do this. I lied. Let's do this. So remember back here, where if f and g are inverses, the derivative of g is the derivative 1 over the derivative f of g of x. You guys remember that? That's what I'm going to use. So I can say since y equals sine inverse x and y equals sine x are inverses, the derivative of sine inverse x is going to equal 1 over sine of sine inverse x. Oh, sorry. Derivative, cosine of sine inverse x. Right? You guys, your facial expressions tell me that's not right. You're not okay. Are you okay or no? So what I did is I'm just using this formula. So f was sine, g was sine inverse. So the derivative of sine inverse is 1 over the derivative of sine inverse. Everybody okay? So that's all I've done is I just plugged my stuff into this formula. The derivative of sine is cosine. So I'm going to go back to my triangle now. And cosine is adjacent divided by hypotenuse, right? Since the theta here is just the angle formed by sine inverse. And that's what we're looking for right there. Again, would I ask you to repeat this proof on a test or quiz? Nah. In second semester, will there be a technique involved where you like do a trigonometric substitution? You have to draw these reference triangles and like do some hooey to make a problem doable? Yeah. So like this idea of being able to draw the triangle and find the side lengths and stuff, valuable skill, but that's much later, and we'll do some practice with it there. Kind of bone up on that trigonometry piece that's maybe feels a little soft still right now. But I want to show you one. All the rest of these proofs can be done similarly, right? Doing cosine inverse starts, the setup is exactly the same way, or tan inverse exactly the same way. So let's do one of these two examples. So I have 1 over sine inverse of x, and I have x times arctan square root x. First things first, arctan is the same as tan inverse, right? They're, for all intents and purposes, they mean the same thing for us. I think there's a slight definitional difference, but like not immaterial to what we're doing. So if you look at 1 over sine inverse of x, take the derivative of that, what do we need to use? Quotient rule. Or you could use a chain rule there too, and just think about that as sine inverse x to the negative 1. You could think about it that way also. It doesn't really matter. I think that that is the easier way to think about it for this particular problem, though. If I have just a straight reciprocal function, I'm going to probably think about it as a chain rule rather than a quotient. But I usually feel like the chain is less work than the quotient rule is. It's less writing anyway. So the derivative of the outside is just that, right? And then times the derivative of the inside, which we know is that. And now maybe there's some cleanup left to do, but like good enough for us. That's a free response question. Does that feel okay? Yes, Lucas. This one right here? Yeah.
I have a question on school.
This guy?
How do you highlight dy over dx? How is that just like
So we, on the previous step, we took the derivative of y cubed. So because when we took the derivative of y, it created dy dx, right?
So
And
whenever you take the derivative of something, when you're done with taking the derivative, dy dx always just pops in.
so if the variable that you're differentiating doesn't match the variable that your derivative is with respect to, so the denominator of my ddx, if the variable I'm taking the derivative of isn't an x, then I get a d whatever dx in addition with my derivative. So if that was the derivative of z or d dx of z cubed, I get 3z squared dz dx. Okay? Or if it was d dt of y cubed, I get a 3y squared dy dt. Does that, you see the mechanics of what's going on there?
Yeah.
Okay. Okay. Is that okay? Better? Okay. All right. F of x equals x arctan square root x. To do the derivative of this, what do you need to use? Okay, chain rule and product rule is correct. In what order? Which one comes first? Nope. Because if I look, it's like f of x times g of x, but inside of that g of x is another function. So to get to the other function, I have to do the product rule first, and then the chain rule will be encountered afterward. Does that make sense? So I have Does everybody feel okay there? The product rule applied that first go. Now the derivative of tan inverse is 1 over 1 plus x squared, but my x here is its own separate function. Here's my chain rule happening. Does that feel okay? I've gone too fast, or I did something you don't quite understand, like slow me down and ask. That's probably the best that we're going to do cleanup wise. But pointing out again, you could be done at this step in a free response setting, right? All the calculus is done at that point. Everything after is just Mr. Cooley cleaning it up a little bit to make it look like something that might appear as a multiple choice answer. Okay. That's it for 3.5. So you have this implicit differentiation piece that we've talked about here over the past 2 lessons, and then these inverse trig function derivatives that we added to our list of derivatives. We have one more set of derivatives to add before we've completed our collection. Our Pokemonic quest to collect them all is nearly the end. I'm going to start 3.6 today because it's going to complete our journey. So we have that the derivative of log base a of x is equal to x 1 over x times the natural log of a. To prove this, so again, remember that we have that, right? So log base a of x and a to the x are inverses. So my log base a of x is like my g, and my a to the x is like my f. So the derivative of a to the x is just a to the x times the natural log of a. That was a derivative rule from 3.4. So f prime of g of x is a to the log base a of x times the natural log of a. Composition of inverses cancel out. And then we're done. Okay. And similarly, if we just make a equal to e, then the derivative of the natural log of x is just 1 over x. So the same idea as above, just with a equal to e. Okay. If we're asked to differentiate the natural log of x cubed plus 1, I notice that this is a chain rule problem where I have a function inside of my natural log. Right? The outer function is the natural log, the inner function is the x cubed plus 1. The derivative of the outside is 1 over the stuff times the derivative of the inside. And the derivative of x cubed plus 1. And what we've presented here below is just the derivative rule for the natural log with the chain rule already kind of built into it. That's all those formulas are. Everybody okay? So let's just kind of continue plowing through some examples using these. If I want to do the derivative of the natural log of sine x, again, I see a chain rule. The outer function is the natural log. The inner function is sine x. So the derivative of the outside is 1 over the inside times the derivative of the inside. Derivative of sine is cosine. 1 over sine times cosine is going to be cosine over sine, which is cotangent. You guys all okay seeing that? Again, am I expecting that you have these basic trig identities memorized, like the quotient rules and reciprocal rules and the basic Pythagoreans? No. The double angles and angle sum and differences? No. Everybody's okay? If I look at the next one, the square root of the natural log of x. Again, I see a chain rule there. The outer function this time is the square root. So we'll think about this as like the natural log of x to the 1/2 So the derivative of the outside is 1/2 times stuff to the negative 1/2, and then times the derivative of the inside. Which is 1/x. I guess what do we have here? We have 1/2x square root natural log x. This is how we'd write that. I want to skip down to example 5. This will be the last one we look at today. If you look at this, what do you see going on? And another chain rule, right? You know what I see going on? I see just 2 chains. We don't need to do quotient rule here. But it's cool, like there's clearly division going on. You know what I'm going to do? I'm going to algebra my way around doing that quotient rule here. Who remembers their properties of logarithms? Those guys look familiar? That's what I'm going to do to make this problem enormously easier. So I'd start by doing a quotient property. Everybody's okay there? And remember that a square root is basically a 1/2 power. So I can then do a power property on top of that. And now I'm ready to take my derivatives. I haven't done a derivative. All I did was do the power property. It allows me to move the exponent to a coefficient, right? So I haven't done any calculus yet. And the derivative of x plus 1 is just 1. The derivative of x minus 2 is just 1. Done. Boy, that made life so much simpler, didn't it? A little bit of algebra beforehand makes the medicine go down. We're going to introduce a technique for dealing with things like we saw in that group 4 problems that I gave you to take the derivative of. Next time, we're going to show you a technique where we can use it to kind of simplify maybe some of those terrible problems that have lots of product and quotient rules inside of them. like if we're looking at this one, this looks like a knife, right? I see a quotient, I see two chains, and I see a product. Yup, that's a lot of stuff going on. We can really knock this down. It's just 3 chains, and it's an algebra before and after. We'll look at that next time, though. For your homework quiz for next time, you guys should be able to do some implicit differentiation stuff. I will not ask about any of the inverse trig rules on the next homework quiz, so don't spend a bunch of time memorizing those today. You do need to spend a bunch of time memorizing them at some point, but not tonight. So next time, implicit differentiation. No inverse trig rules on that. Everybody's good? Okay. We have the rest of 3.6. 3.7 is like one type of problem that we've already talked about. And then 3.10, and we're looking at test 3 coming up here probably end of next week. I know you blink and it's there already. Kate did a double take on it. She's like, what, already? I don't know what to tell you guys. This next one is usually the best one for first semester, the best test for students, because it's almost, the entire thing is just, can you do derivatives? Because you have now all the derivative rules, if you have them all memorized, and you know how to like look at a problem and do the sequence, like you're able to do stuff in the right order, things usually go really, really well. If you're a little shaky on that stuff, it can be kind of a headache, but there's not a lot conceptually going on here that, you know, it's very simple, pushy, like algebra heavy. Can you do the symbols? But that's my story, guys. We'll stop here.